Bismillahirrahmanirrahim. In the last few lectures, we discussed regarding fixed bias, voltage divider bias, and emitter bias. Today, we will discuss about another kind of biasing technique which need only one power supply, and it is known as the base bias. Okay, base bias. So today we are going to discuss base bias. So the circuit diagram is, we have the transistor, NPN transistor like this, okay, and we have a power supply VCC, usually it is a positive power supply, and we have RC, and we will use the same power supply to bias the base emitter junction also, and this is RP. Okay, so we will use the same power supply, and this biasing technique is known as the base bias. As you know that we will write the Kirchhoff law at both sides. So the input side, actually this is the input side, you can say this is the input side, and whatever I am seeing from the output, that is the output side. Okay, so we will write the Kirchhoff law at the input side. So the input side, the power supply is starting from here. You can see the loop we can take, because you see here it is going here and it is going to the ground. So we are starting from the ground. You can see there is a ground here. Since this end is positive, the ground is connected to negative. So we are starting from the ground and going to the ground. Okay, so we will start from the ground. So this is known as the loop 1. So we will write the KVL at loop 1. Okay, now when we start from the ground, we can see first the negative. So it is negative VCC, and you know that the current IB is going down, right, or it is going into the base. So since the current is going into the RB, whenever the current enters, here it is positive and here it is negative. So plus IB RB, then you know that base emitter junction is usually 0.7 volt. So plus 0.7 is equal to 0. So from the above equation, we will get IB is equal to VCC minus 0.7 divided by RB. So this is the way to find the IB. And once you get the IB, you can find the IC. IC is beta DC times IB. Okay, so this is the equation. Now we will consider the another loop, that is we will take the loop like this. It is going to the ground. You can see here it is starting from the ground and it is going to the ground, so which is known as the loop 2. So the KVL at loop 2. Okay, so we will take the KVL at loop 2. So we are starting from the ground. You can see it is minus VCC, then the current IC is moving down. So here it is plus and this is minus. So plus IC RC. Since the current is going down, here is plus and minus, this is VCE. So plus VCE, then nothing else, this is equal to 0. So we can find VCE from this. VCE is equal to VCC minus IC into RC. So this is another equation to find. So we got the equation to find AC and we got the equation to find VCE. Now we can draw the load line here itself. We can draw the load line. See, in the load line, you know the x-axis is VCE and the y-axis is IC, and we have the transistor characteristics like this. Okay, now we can number the equations first. This is IB, equation for IB is equation 1, this is equation 2, and this is equation 3. Now for load line, actually we will take equation 3. Okay, now in equation 3, okay, this is I'm separating it. So in equation 3, to find the x-intercept, how to find the x-intercept? To find the x-intercept, you have to put y equal to 0. That is, put y equal to 0. That means IC is equal to 0. So we will put IC equal to 0, which implies VCE is equal to VCC. Okay, so you got the point, VCE equal to VCC. Now using the same equation 3, you will find the y-intercept by putting x is equal to 0. That means you will put VCE equal to 0 in the equation 3. So as in the same procedure as in the previous biasing also cases also. Now we will find IC or IC sat is equal to VCC over RC. So we got two things, that is we got the x-intercept and we got the y-intercept. So we have the x-intercept as VCE equal to VCC, and y-intercept we got IC sat equal to VCC over RC. Now we can draw the load line. So load line will be like this. Okay, so this is how to draw the load line. Okay, now we will do a problem based on this. So the problem is determine how much Q point, that is the Q point is usually denoted as x-axis, VCE and IC for the circuit in figure below change over temperature, given that beta DC increases from 100 to 200, and it is here. So you can see here the beta DC is changing from 100 to 200. Okay, and also show it on the load line. Okay, we want to show it on the load line, and the circuit is given. You have the circuit VCC, this is RC, and you have something known as RB. It is taken from VCC. Okay, now we have the equation for IC as IC is equal to beta DC times IB, which is equal to beta DC times, what is IB? IB we have already find here. You can see the equation 1. Okay, that is nothing but VCC minus 0.7 over RB. This is the IB, and IB into beta will give you IC. Okay, this is our equation. Now we have VCE equal to VCC minus IC RC. So this is our another equation. We want to find these both. Okay, as per question you can see we want to find VCE and IC. Okay, now for beta DC equal to 100 we will calculate, and also we will calculate the same thing for beta DC equal to 200. Okay, so for beta DC is equal to 100, we will call this is IC1. Okay, IC1 is equal to, you know, it is nothing but beta is 100, and this is given as 12 volt, and RC is given as 560 ohm, and this is RB is given as 330 kilo ohm. Okay, so we will get it as 12 minus 0.7 over 330 kilo ohm. Okay, so this much volt minus, so this is nothing but 3.42 milliampere. Okay, so we are getting the IC like this. And also VCE, we can say it is VCE1 because we are talking about beta equal to 100. So it is nothing but VCC minus ICRC. So you can use the equations here. Okay, so you can use the equation I have shown in this slide. So it is nothing but 12 minus 3.42 milliampere multiplied by 560 ohm. Okay, this is 12 volt. So you will get here it as 10.1 volt. So you got both, you got for beta equal to 100, you can see I have used beta is equal to 100 here. I got the IC and I got the VCE. Okay, now we will find for beta equal to 200. For beta equal to 200, you can see IC is equal to, we can say IC2. Okay, for beta is equal to 200. It is nothing but 200 multiplied by 12 minus 0.7 over this volt minus 330 kilo ohm. So you will get it as 6.84 milliampere. Okay, you can see the IC has been changed. Previously it was 3.42, now it becomes 6.48. and VCE 2, it is nothing but 12 minus ICRC, that means 6.84 milliampere into 560 ohms. This is 12 volt. Okay, 12 volt. Okay, so this is nothing but 8.17 volt. So you can see here there is a significant change in the IC. So for beta equal to 200, I have used 200 here, then you got the IC as and VCE, which is significantly different from the old value. Now we will calculate what is the percentage change in IC. Okay, so the percentage change in IC, delta IC in percentage, we can calculate like this: IC2 minus IC1 divided by IC1. Okay, this is equal to 6.84. you can see the new value is 6.84 and the old value is 3.42 milliamps. So 6.84 milliamps minus 3.42 milliamps over 3.42 milliamps into 100. Okay, so you will get the change as 100%. That means your IC has been changed drastically. That means this kind of biasing technique is one of the worst biasing technique, we can say. Now delta VCE is equal to VCE2 minus VCE1 over VCE1, which is equal to 8.17 minus 10.1 volt divided by 10.1 volt into 100. You can get it as minus 19.1%. So you can see here this is 100%, which is positive 100. That means this increases, IC increases and VCE decreases. Okay, so you can see there is a drastic change, a significant change in IC and VCE. Now we can say that this biasing technique, our conclusion is that the base bias. Okay, the name of the biasing technique that we have discussed now is known as base bias. Base bias is not a stable biasing technique. Okay, so base bias is not a stable biasing technique. Now we will show the same thing in the load line. Load line, you can see this is our load line. We have x-axis VCE and y-axis IC, and we have already discussed this is the load line. We will get here VCC. VCC is 12 volt, and what is our IC sat? IC sat is equal to, we have taken the voltage of 12 volt, 12 by 560, right? So it is nothing but 12 by 560, it is nothing but 21.4 milliampere. So you will get VCC over RC, which is equal to, which is nothing but 21.42 milliampere. Okay, this is 21.42 milliampere. Now at first we will mark the Q point, initial Q point IC1 and VCE1. So VCE1 was some 10.1 volt, I think so, right? It is nothing but 10.1 volt. So you can say this is 10.1 volt. So we have, this is 12, we have 12 here, so 10.1 may be here, this is 10.1 volt. So this was our VCE1, and corresponding IC was something like 6.84 milliampere. This is IC1. Now due to the change in the temperature, you can see here the new value has been shifted here, and it become VCE2 is equal to 8.17 volt, and IC2 become 6.84. sorry, the previous one is not 6.84, it is 3.42 milliampere, and now it becomes 6.84 milliampere. This is IC2. Okay, so this is VC, you can say that this is VCE1 and IC1. This is our Q point for which beta equal to 100. Okay, now the Q point has been shifted to VCE2 and IC2. This is the case with beta equal to 200. Okay, so you can see here when beta changes from 100 to 200, what happens? The Q point has been shifted. The Q point has been shifted from this point to the new point. Okay, so that's why this is unstable bias. Okay, I hope that this is clear. Now we want to make it stable, right? So for making it stable, we will do something. As you have observed in the previous lectures, that whenever there is a resistor at the emitter, the biasing technique become more stable. Now we will add a emitter resistor to this biasing technique, and you know this, we have, this is the biasing technique that we have discussed now. We have VCC, this is plus, and the minus, you can say minus is going to ground. Okay, and we have something like this, this is RP. Okay, this was the biasing technique. Now what we will do, we will add a resistor here. So when I add a resistor here, this become more stable. Now we will see what is this bias? The name of this bias is the emitter feedback bias. Okay, emitter feedback biasing. Okay, so we have previously taken the base bias. When we add a resistor Re to the base bias, then it become emitter feedback bias and it become more stable. So we will see how it become stable. So first of all, we will write the Kirchhoff laws. So we will take the input side. You can see here the input side. We have, this is the input side. We can say this is the input side. We will take this as the loop 1 because we will start from the ground and we will end at the ground. Okay, so when I start from the ground, I first see minus, so it become minus VCC. Okay, so I will take it as loop 1. We will say it as loop 1. So we will write the KVL along loop 1. It's loop 1. Now become minus VCC. Then you know that the current is going inside, that is IB, so it is plus minus, so it become plus IB RB. Then you can see something known as 0.7, right? And also there is a current here which is IC, and this current through the RE is IE, which is approximately equal to IC. So since the current enters, the polarity at the RE become plus and minus. So we have now, after finishing IB/RB, we have another that is 0.7 along the base emitter junction. So it becomes 0.7, then it become plus IE into RE, right? Then we reach the ground, so we completed the loop, so it become 0. Now we have this biasing technique. Now we have seen that IC is approximately equal to IE. So in this equation we will replace IE with IC. So take this equation, so it becomes minus VCC plus, and you so also you know that IB is equal to IC over beta DC. So we will replace IB with IC over beta DC. IC over beta DC. So it become IC over beta DC, then into RB plus 0.7 plus IC into RE. You can see here this is equal to 0. So minus VCC plus IC, I will take IC outside, it become RB over beta DC plus RE plus 0.7 equal to 0. So what is the equation for IC? IC is equal to VCC minus 0.7 over RE plus RB over beta DC. Okay, this is the equation for emitter bias, emitter feedback bias. Okay, now we will find the VCE also. So for finding VCE, to find VCE, we will again draw the circuit. You can see here VCC, and this is plus VCC, and the minus of this is grounded. Okay, and we have RE, and here it is ground. Now we'll have something known as RB here. Now we will take a loop here at the output side. This is the output side. Okay, so output side we will take a loop here. This is VCE. Now this is the loop. So the loop start from the ground and it is going to ground. So we will write the Kirchhoff law here. You can see we'll start from the ground, so starting with minus, so KVL, we can say this is loop 2. okay, KVL along loop 2 is minus VCC. Then this is RC, you know the current IC is going down, so here plus and minus, so plus IC RC, and you can see this is plus along VCE, so it is plus VCE, and the current is going down and it is IE, but IE is approximately equal to IC, right? Anyway, I will write it as, now the current is going down, as so the polarity become plus and minus, so plus IE into RE is equal to 0, but we know that IE is, but we know that IC is approximately equal to IE, so we will replace this IE with IC. Now we will rewrite the equation, so minus VCC plus IC RC plus VCE plus IC RE is equal to 0. So what is this IC? So IC is equal to, not IC, we are going to find VCE. okay, so we have VCE, which is equal to VCC minus IC into RC plus RE. So this is the equation. So these are the equations. So we will conclude the equations related to emitter feedback bias, or what are the equations? At first we have discussed regarding IC. okay, so this is the first equation, that means IC is equal to VCC minus 0.7 divided by RE plus RB over beta DC. Am I correct? Right? RB over beta DC. So this is the equation. And VCE is given as VCE is equal to VCC minus IC into RC plus RE. So these are the two equations related to the emitter bias. Now we will talk about the stability of the emitter bias. okay, so stability, okay, we will talk about the stability. You know that whenever the temperature increases, what will happen to beta DC? Beta DC also increases. When beta DC increases, the value of the current IC increases, because IC is equal to beta times IB. As IC increases, you know that whenever this current IC increases, the voltage here, that means the voltage at the emitter VE, which is equal to IERE, we can say approximately equal to VE, which is approximately equal to ICRE, will also increase. Whenever VE increases, you see here the voltage at the emitter is increasing. It will oppose the increase in IB, or we can say that it will reduce the IB. So this will cause the reduction in IB, and it will cause the decrease in IC. That means IC will try to decrease. So we can say that whenever there is a change in the temperature, immediately uh, IC will try to increase, but IC will immediately come down, and it will maintain almost the same value, so that this biasing technique is stable. Okay, this biasing technique is stable. Okay, I hope that this is clear to you. Now we will explain the load line for the same. So we have the equation. I will rewrite the equation. IC equal to VCC minus 0.7 over RE plus RB over beta DC, and we have VCE equal to VCC minus IC into RC plus RE. Okay, now we will draw the load line. So we know that x-axis is VCE and y-axis is IC. Okay, now we will take this equation, equation number 2, and the previous one, that is the equation number 1. So we will take the equation number 2. Okay, so to find the x-intercept, to obtain the x-intercept, you have to put y equal to 0. That means you have to put IC equal to 0. That means VCE become VCC. So you got 1 point VCC. So VCE is equal to VCC here, or we can say that this is the x-intercept. Okay, now to obtain the y-intercept, you have to put x is equal to 0. That means you have to put VCE equal to 0, which implies IC equal to VCC over RC plus RE. So you will get the IC sat here, this point. IC sat is equal to VCC over RC plus RE. Now you got 2 points. Now you can join this. This is the load line. And also you can draw the transistor characteristics. You can show the transistor characteristics like this. These are all the transistor characteristics. Okay, lines to represent the transistor characteristics. So I hope that this is clear, and you can mark the Q point. You can mark the Q point as in the previous case somewhere. Suppose you have VCE, this is your VCE, and VCE, what is the equation? It is nothing but VCC minus IC into RC plus RE. This is your point, VCE, and we can say this is Q point, and another one IC. You can find the IC. You can say that this IC is nothing but your, according to this equation, IC is VCC minus 0.7 over RE plus RB over beta DC. Okay, so this is how you can find the IC and VCE, or the Q point. Okay, I hope that this is clear. Thank you.